Integration is another important idea for NMR spectroscopy. So integration is really about the size of the peak. And size of the peak is not its height, it's not its width, but it's a combination of those. It's really the area under the curve of the peak. So different types of peaks can, a really tall yet narrow peak may be no bigger in area than a peak like that that's short. So don't just look at the peak height, although that's typically the easiest thing to do. It's really about the area under the peak. Turns out, since visually it's hard to look at a peak and say, oh, that one's bigger or smaller, we let the computer that's running the spectrometer determine what the area under the curve is. And so it integrates, it sums up the areas, it does a trapezoid approximation, and this gives us an area under the curve. The size of the peak represents the number of hydrogens that are contributing to that area. So we'll look at the integration values relative to one another, the integrated values relative to each other, and we'll often reduce these fractions. So you might find one peak has an area of 2.5 and another one is 5.0. Well, clearly we don't have 2.5 hydrogens. You can't have a half hydrogen. So maybe you would say, well, these are really just a 1 to 2 ratio. Or maybe the true ratio is 2 to 4. But we'll express it in a whole number value because we can't have partial hydrogens. Let's see a little bit how this works. We'll look at two sample spectra. And here is an example. This is a molecule acetophenone. Let's draw in all the hydrogens. These three hydrogens by symmetry are identical, so they will show up, all those signals will show up together as 3 hydrogens, 3H, and here they are. They're right down here. This is a 3H. It's a singlet. Notice there are no neighboring hydrogens. If there were, they'd be on that carbon, but that carbon already has 4 bonds. There are no hydrogens, so n equals 0. Therefore, its multiplicity equals 1, and it is indeed a singlet. It's 3 hydrogens, and you're given that value. That has a relative intensity of 3. Now, what else do we have? We have hydrogens around this ring. And as it turns out, we have 5 more hydrogens, and they're all here, 2 plus 3. This is all 5 of our additional hydrogens. Now, those 5 hydrogens are not all identical. They're all in the benzene ring. They ought to show up in the, problems with that, 6.5 to 8 ppm. That's their chemical shift, and that's where they show up in the 6.5 to 8 window. All 5 hydrogens are there. As it turns out, these 2 hydrogens show up differently. They're the ones that show up, let's call that at 7.8 ppm. And these 3 hydrogens show up more at, let's call it 7.4 ppm. Now, I don't want to get into why some show up one place and not another place, but the point is all the hydrogens are there. This molecule has 8 hydrogens. 5 of them are here off the benzene ring, right in the correct chemical shift region, and 3 of them are over here in the 2 to 3 range, which is about what we'd expect. So all our hydrogens are present and accounted for, and that's always going to be the case. So when we're trying to solve structures, it's very important to look at your integrations. Oh, I've got 3 here, 2. I'm going to have 8 hydrogens total. Okay, let's look at another example. Here's ethyl ether. So ethyl ether has 10 hydrogens. So our integration needs to say that we have 10 hydrogens. Turns out 6 of them are on these 2 methyl groups, which by symmetry show up together. They're a triplet. We've talked about their multiplicity. So we have 6 H's over here and 4 H's over here. All 10 hydrogens are present. Now, if we were running this spectrum, we wouldn't know that these are necessarily 10 hydrogens. What we would know is that this peak, it will be 1.5 times bigger than this peak. So, since you can't have a half hydrogen, you might say, okay, let's multiply these by 2. These would be it's not in 1 to 1.5, we could maybe call it a 2 to 3 ratio, or some multiple of 2 to 3. It could be a 4 to 6 ratio. As it turns out, it is a 4 to 6 ratio. I'm kind of cheating because we already know the structure of the molecule. But it's going to be some multiple of this, what we would see as a 1.5, a 1 to 1.5 ratio. Now in this case, when I give you spectra, I will give you the correct number of hydrogens. I won't ask you to think about all the different possible values. I'll give you the correct numbers. But it's important to understand, when you take the spectrum, you don't always know what the structure is. So you don't know what the ratio of the area should be. All you can do is reduce it to, well, this is a 1 to 1.5. But there is a real number in there. So that's how we use integration. It helps us keep track of how many hydrogens we have in our molecule.